Tree of Knowledge is an online platform where social science researchers can upload their dataset, make an exact model of the social system they are studying, and gain many insights about the exact dynamics driving this system. But how does this lead to the creation of the world's first fundamental theory of human behaviour? And how does this enable researchers to create accurate simulations of any social system? We will answer these questions in this video. The most common way of gaining knowledge in the social sciences is from a dataset that was obtained by a study. The knowledge is extracted by fitting a statistical model to the dataset, which will give you some insights, here illustrated by leaves. Over the years, many social scientists have analysed many different datasets this way, giving us many different insights. Unfortunately, the replication crisis has shown us that insights that are based on only a single dataset are not very robust. A meta-analysis is more robust than a simple model, as it combines the learnings from multiple datasets. Unfortunately, however, the included datasets have to come from extremely similar studies. This severely limits the number of datasets that can be included and makes it likely for there to be common biases and other problems with the data. Meta-analyses, therefore, aren't particularly robust either. In this video, I would like to present to you the new type of model that is used by the statistics platform Tree of Knowledge. Tree of Knowledge uses a completely new approach to statistical modelling that combines the learnings from very different datasets. The included datasets are not even limited to studies. You can also include any of the millions of observational datasets that are openly available. As more and more datasets are added to Tree of Knowledge, this model will continue to grow in robustness, accuracy, and scope. But how does it work? How can a single model be trained on datasets covering areas as diverse as people's voting behaviour, business deals, sports, and much more? Well, the idea is inspired by physics. At the core of physics models are fundamental agents for generic objects such as solids, fluids, and light. These fundamental agents are very powerful. The agent for modelling solids can, for example, be used to exactly model any mechanical system. To model the cogwheels, for example, an engineer will make a 3D model of these cogwheels out of solids. We can automatically simulate this system by letting each cog simply follow the behaviour rules for solids. We can use the same solid agent for accurately simulating arches, with each stone being an agent. Same for pendulums. Any mechanical system can be accurately modelled by just bringing solid agents into the right shape and configuration. Tree of Knowledge also uses such fundamental agents. These are the fundamental agents for modelling humans, countries, companies, or other actors in social systems. You can model a system with the person agent by putting the agents into the right configuration and specifying details such as the people's age and character. Using the same fundamental agent, you can also model people queuing. Really, any social system can be modelled by putting these fundamental agents into the right configuration. This way, we have a single model, the behaviour rules of the person agent, which is used for modelling all these different datasets. Let's look at the agents in more detail. There is a crucial difference between the agents in social systems and to the agents in physical systems. While we know the exact behaviour rules of the physics agents, we do not know the behaviour rules for the social agents. Well, in some cases, we know the exact rules. For example, we know that the age of a person increases by 1 each year. And we know how to calculate a country's population as a function of its birth rate, death rate, and immigration. For the other rules, which we are not sure about, we have statistical functions. Such a statistical function, say the function for calculating someone's extroversion, could depend on any of the person's own attributes. other people's attributes, or even events from the past. Once we specify such a function, Tree of Knowledge will automatically fit this function to the data from the studies using Bayesian inference. And it is also fitted to the observational datasets using simulation-based inference. Then, Bayesian statistics is used to combine the parameter estimates from all the different datasets. And as a final step, it is also used to evaluate the fully fitted function. Concerning the evaluation of statistical functions, the statistical function we just now trained was just a guess. Let's say we guessed that extroversion depends on someone's energy levels, their familiarity with the surrounding people, and the unknown weight parameters which we just now learned. In truth, we don't know if this function is correct. Extroversion might depend on very different things. With Tree of Knowledge, it is easy to exchange our guess with a new function that depends on different variables and have the new function automatically trained and evaluated on all datasets. Here again, the software first automatically fits the new function on all datasets. Then it checks whether the person agent with the new fitted rule now produces more accurate models. In other words, it checks whether the new agent with the new rule does a better job at mimicking the behavior of the real people captured in all these different datasets. If it does a better job, we keep it. As we continue to try out different rules, we will find increasingly good ones. We can also try changing sets of rules. At the end, we will have found the best possible set of behavior rules for people. This is an incredibly powerful thing. Some people consider it the holy grail of social sciences. The person agent has been shown to accurately model humans in hundreds, maybe thousands, of different circumstances and settings. It has therefore proven itself to accurately simulate people in any circumstance. In short, it's an accurate theory of human behavior. We can go through a similar process for finding the best possible behavior rules for the other social agents too. With these fundamental agents, we can now accurately simulate any existing or hypothetical social system. To understand how powerful these simulations of social systems can be, let's do a brief thought experiment and imagine what it would be like if engineers had to work with the limited tools available to social scientists. I.e., what if engineers were limited to analyzing individual datasets, just like social scientists? To, for example, determine if a building will collapse in an earthquake or not, a structural engineer would first need to obtain a dataset on collapsed buildings. You can get such a dataset, for example, from a site that has been devastated by an earthquake. We can go around, look at each building, and record things like its height, the wall thickness, what material it is made of, and whether it survived the earthquake or not. Alternatively, we could get such a dataset from experiments. Now, if we plot the data on a scatter plot, we see that the small buildings with the thick walls in the bottom right-hand corner had a better chance of surviving the earthquake. And this is what the resulting model looks like. It predicts small buildings with thick walls to survive. So, if an architect presents us with his design for a school gym, we, as structural engineers, would check the wall thickness and height of the building. For the values here, the model predicts the building to be stable, so we give this design our go-ahead. Sounds like a good approach, no? Well, what structural engineers do in reality is somewhat different. They use the solid agent to make an exact model of all the building's structural components. And then simulate various kinds of earthquakes on this model. These simulations capture the exact dynamics of every structural element. In this example here, we can see that the walls survived as predicted, but the roof collapsed. In general, statistical models that just look at a few macroscopic variables, such as height and wall thickness, are fairly approximate and crude tools and cannot capture all the complex dynamics and interplays that occur in reality. You can only make good predictions of complex systems with a bespoke micro-simulation model that captures all the interactions of the individual components. These micro-simulation models, therefore, produce vastly more reliable predictions. The fundamental physics agents don't only allow engineers to make exact models of buildings. The same agents are used to model systems in all areas of engineering. These exact micro-simulations are essential to modern engineering. The fundamental agents give engineers the power to make an exact model of any mechanical system in any setting, without requiring any prior experience or data about the system. These models are therefore used primarily for determining the properties of new products, testing their failure modes, and optimizing the product without having to create a single prototype. This ability to create accurate simulations of previously unseen systems is very powerful. It is fair to say that without it, most modern technology wouldn't exist. In short, the physics agents have revolutionized mechanical engineering. We believe that the social agents could revolutionize social engineering in the same way. With the agents we optimized earlier, we can accurately model and simulate any social system. We could, for example, predict what would happen if a certain law was introduced, or what would happen if a new bus lane opened up, or how countries' economies and international relations might change over time. With the fundamental agents, researchers get the ability to accurately simulate absolutely any social system by just placing the social agents that make up the system in the right configuration and specifying their details, such as their age, character, etc. With conventional statistical models, on the other hand, we can only model types of systems that have been observed in the real world and for which we have an existing dataset. The ability to accurately simulate completely new, previously unseen systems is very powerful. It allows researchers and advisors to quickly test and iterate through different social system designs without having to make a single experiment. In short, the ability to accurately simulate mechanical systems has been the key to creating practically all modern technology. We believe that the accurate simulations of social systems could lead to similarly advanced engineering, giving us, for example, more efficient laws, institutions, and welfare. There is only one remaining problem. For the physics agents, we know that their behaviour rules are 100% accurate. For the human agent, we might not be able to reach this level of accuracy. Even after all the optimizing and improving of behaviour rules, we might only end up with a 94% accuracy. 94% is quite good, but it still leaves us a little uneasy about how much we can trust the predictions made by the simulations. Fortunately, this problem has been solved. Instead of just running a single simulation, the software runs thousands of possible simulations. Each simulation weighted with the probability of reality unfolding this way. So, for any simulation metric, say the happiness of person 1, we'll have a distribution of simulation outcomes coming from the different simulations. In other words, we can now determine the probability of any real-world outcome. The distribution of outcomes accurately reflects the true uncertainty, which we have due to our lack of understanding and lack of data. The underlying Bayesian framework makes it possible. It captures the uncertainty we have due to lack of data and understanding in the parameters of the agent's rules, and accurately propagates this uncertainty through any simulation. So, as we get more data and the agent's rules improve, the uncertainties in the parameters decrease, and as a consequence, the uncertainty in the simulations decreases as well. In summary, these probabilistic simulations allow us to do the exact same optimizing and inspecting of social systems, just in a probabilistic fashion. We can do the same sophisticated engineering, while always keeping track of the true uncertainty. And we have to remember that the predictions made by these simulations are the most accurate and least uncertain predictions that could possibly be made, as they come from the only model that has been trained and evaluated on hundreds of different datasets. As time goes by and new systems are modelled, the accuracy, scope and robustness of Tree of Knowledge will continue to grow.